Welcome back to the deep dive. You gave us the sources, the patent applications, the schematics, all that dense research, and our mission is, as always, to give you the shortest path to really understanding it. We cut through the jargon so you can get right to the genius. Today, we're looking at what happens when you combine, well, power generation with the sheer scale of a suspension bridge. Our source material describes this really audacious piece of German engineering. It's called a stationary sky, wind, and water power system, or in the original German, a stationär Seil-Textilwind- und Stromungskraftanlage.
Which is quite a mouthful.
Right. But just forget the windmill you see on a hilltop. This is something else entirely. It's a gigantic, flexible turbine made of textile, and it's suspended across an entire valley.
Okay, let's unpack this. Our mission here is to get the audacity of it. I mean, how do you even span a valley with a massive generator? And more importantly, how do you use something as, flexible as sailcloth for the blades of a power plant?
It really is a paradigm shift. It is. This deep dive is about the innovations that make that flexibility stable and how gravity becomes a tool.
Well, you're right. We're so conditioned to think of power generation as these massive, rigid things, steel, concrete, super stressed composites. This invention, though, it frames the challenge completely differently. It's all about flexibility and scale. It's designed to generate huge amounts of power from wind and sometimes water currents, too, using these enormous textile surfaces that are fixed between two natural anchor points, like mountains.
So not a tower.
No tower at all.
That immediately sets the scale. It's infrastructure. The sources even compare the support structure to a suspension bridge. They use the term Hängebrückenart.
Precisely. And the backbone of this whole macroengineering project is one single, immense main carrying cable, the Haupttragseil, as the documents call it.
So everything hangs off that one cable?
Everything. It's the highway for the whole system.
Yeah.
And the schematics show how versatile it is. You can use 2 pylons, 3, whatever the terrain demands.
Okay, so they solved the spanning the gap problem with classic bridge engineering. But the real genius, the thing we need to focus on, is what's happening in the middle of that span. They had to solve 2 problems at once, right? One, how to make turbine blades out of huge sheets of fabric. And 2, how to stabilize the generator without a bunch of complex, high-maintenance controls.
And here's where it gets really interesting. Think about a traditional wind turbine. The whole thing spins, right? That turns the generator, makes electricity, and the entire assembly has to be actively pointed or yawed into the wind with motors.
Which is complicated. It's another system that can break down.
Exactly. This design flips that completely on its head.
Yeah.
In their system, the generator stator is fixed. It does not rotate.
It doesn't move.
Stays perfectly still. Only the huge flexible turbine rotor spins around the axis. And to do that, they house the generator inside this rigid structure called the torsion tube, the torsion-stiff. Now this tube, it encloses the main cable, but it's built not to rotate. The stator, the part that actually makes the electricity, is fixed to this non-rotating tube with 4 big, sturdy arms.
Okay, now hold on. That's the part that just seems to defy logic. If the stator is fixed, how does it stay pointed the right way? And the documents say the stator is intentionally heavier than the entire turbine. You're adding all this dead weight to the middle of a suspended cable. That feels wrong.
And that intentional weight, that's the whole trick. That is the breakthrough stabilization mechanism. They're using basic physics to get rid of complex machinery. Well, because the stator is so much heavier than the rotating blades, and because it's locked onto that non-rotating tube, gravity just takes over.
Wait. So the generator is basically a giant self-aligning pendulum?
Precisely. That's a perfect way to put it. Think of it like a weighted keel on a sailboat, or maybe one of those roly-poly toys that always pops back up. Its own weight means the heavy, fixed stator automatically aligns the whole system downward. The German is stable nach unten aus, anytime the wind shifts.
Let's just pause on that for a second. That's a huge deal. Normally you've got motors, sensors, gearboxes, all just to keep the turbine pointed into the wind. Active yaw control.
Right.
And the system just throws all of that away. It replaces all that complexity, the stuff that breaks in a storm, with gravity.
That's the key takeaway. The engineers are very clear. This passive, gravity-based stabilization means no further complex upper or lower securing systems are required. The pipe and the main cable handle the load. The mass handles the alignment.
So they've traded electrical complexity for physical simplicity. And weight.
A brilliant inversion of how we normally think about wind power engineering.
It's genius. They made weight the enemy of most structural engineering, the system's most reliable feature. Okay, so stability is solved, but that leaves the other massive problem. How do you stop a football field-sized piece of fabric from just shredding itself to pieces at high speed? Let's talk about the blades.
Right, so we move from static stability to dynamic stress. Using flexible materials like sailcloth or canvas gives you advantages. For sure, lighter rotating mass, probably lower costs. But it introduces this monstrous structural problem. The sources mention designs that can handle 20,000 square meters per blade.
20,000, that's like 4 football fields of fabric spinning.
Correct. And that huge surface has to fight centrifugal force trying to rip it apart, plus all the atmospheric stress, and it still has to hold a perfect aerodynamic shape.
Any little flutter or fold, and it's useless.
Instantly. The material itself wants to collapse.
So how did they give it that integrity? Was it just a matter of using really, really strong cables?
It's much more nuanced than that. It's a multi-layered approach, a 3-tiered internal structure that works like a skeleton, muscle, and skin all at once. The first layer is the skeleton. These are the crossbars or cristangen. Think of them as ribs inside the blade.
Okay.
They run across the fabric, and their job is to stop that huge surface from just folding in on itself. They maintain the aerodynamic profile and spread the wind load evenly. They stop it from buckling.
Got it. So that keeps the blade's shape. But what about the fabric itself? The constant stretching from wind pressure and all that centrifugal force?
That brings us to layer 2, the embracing cables. The German is umlaufende Seil, which you could sort of translate as hugging cables.
Hugging cables.
Yeah, and that's what they do. They wrap around the outside of the textile, hugging the surface.
So they act like an external reinforcement.
Exactly right. They take the stress off the fabric itself. They stop it from overstretching in one spot, which is how tiers start. All that heavy wind pressure gets transferred by the cables directly into the main axis and the pylons. So the fabric catches the wind, but the cables take the punishment. It hugely increases the lifespan of the blades.
Okay, so we have an internal skeleton and an external armor. But what about the spinning? The forces trying to just fling the ends of the blades off into the valley, and the twisting forces, the Verwindung.
That's the third and final layer, the diagonal and transverse tension cables, the Abspan Seil. These are the muscle. They connect the blades directly to the central axis. Their whole job is to fight those massive centrifugal forces from the rotation. They stop the blades from twisting violently or starting to flutter, what the Germans call flattern at high speeds. They keep every inch of that fabric in perfect high-tension alignment. It turns a flexible cloth into a rock-solid airfoil.
A 3-tiered system. Skeleton, armor, and muscle. That's what turns cloth into a power source. Okay, let's put it all together. Walk us through the sequence. First, wind hits the textile surface, rotor starts to spin.
Right.
Second, that whole complex system of cables and bars keeps the blade's shape against all that stress.
Okay.
Third, that spinning motion gets transferred to the generator's rotor, which is spinning freely around that fixed torsion tube.
And fourth, the generator's stator, that heavy-weighted core, it just hangs there, perfectly stable because of its weight and that rigid tube. It's the anchor in the storm.
So what happens if the wind totally shifts, say by 90, even 180 degrees?
And that's where the passive genius just shines. The turbine itself starts to turn into the new wind direction, but the heavy stator automatically corrects itself. It keeps the whole generator assembly pointed straight down.
No motors, no computers.
Just gravity.
Yeah.
The entire system realigns itself automatically. And we connect this to the bigger picture. What the engineers are building here isn't just a new wind turbine. It's a whole different class of utility-scale energy infrastructure. This design lets you build at an unprecedented scale in places where a normal tower-based turbine would be impossible. Gorges, deep offshore channels, you name it.
And the cost must be a huge factor, right? Using high-tech fabric instead of thousands of tons of steel and fiberglass for the blades has to bring down the cost of the rotating mass.
Absolutely. Less weight spending means less stress on the supports. Probably cheaper manufacturing, definitely easier installation in remote spots. And the source even points out the functional flexibility.
How so?
Well, depending on the site, you could place it low enough to capture both wind and water currents at the same time. That's a synergy that's almost impossible to get with conventional designs.
That really broadens the potential. The sources even mention other variations, right? Like a solid block design, almost like a ship's turbine, or setting up several of them in parallel across a really wide valley.
Exactly. It's conceived as a truly modular, scalable solution.
So what does this all mean? If we boil it down, the 2 key takeaways for you, the listener, are pretty clear. First, just the ingenuity of using these massive, flexible textile surfaces. a material that only works because of that incredibly complex three-layer system of cables and rods that turns cloth into a rigid dynamic power source.
And second, that brilliant self-stabilizing generator. They took complicated, failure-prone active yaw systems, all those motors and sensors, and replaced them with the simple, unchanging reliability of gravity. Making the stator heavier made the whole system smarter. And that raises a really important question for you to think about. This design achieves stability by making the non-moving fixed core the heaviest part of the system. So, given that success balancing a heavy, fixed component against a lightweight, moving one where else in large-scale infrastructure could this inverse approach be used? A gravity-reliant core that stabilizes a dynamic outer layer. Think beyond just energy. Could this simplify how we design massive telescopes? Or maybe even structures that have to withstand really extreme, unpredictable forces? It makes you really think about the power of passive stabilization.
An outstanding thought to leave you with. That's a wrap on this deep dive into giant flexible wind power and the elegance of simple physics. Thanks for joining us. We'll see you next time.